So I'm happy to welcome next presenter, David J. Birnbaum, and he will tell you something about implementing of quite complex algorithm in XSLT 3.0. Thank you.
Thank you. Can you all hear me with the microphone? If you can't hear me, raise your hand. All right, thank you. In the context of one of the welcoming addresses about the tension between the imposter syndrome and overconfidence, I'd like to introduce myself as someone who is not a computer scientist and is going nonetheless to talk about dynamic programming in XSLT. I enjoyed working on this. I learned things I didn't know before. I hope it will be interesting to the rest of you. The outline of today's presentation is going to begin with an introduction of what sequence alignment is and why people do it. And I'm going to talk about the role of scoring in alignment. Then I'll introduce the method that was employed here. The background technology is dynamic programming, which has been around since the 50s. And the algorithm, the Needleman Wunsch algorithm for sequence alignment, has been around now for 50 years. So this is an anniversary presentation. Dynamic programming poses challenges for XSLT because of the type of language XSLT is. So I will talk about how one reconciles that tension and how one implements a dynamic programming algorithm working within the limitations, or let's say the structural properties of XSLT. I will propose a small change in the way the algorithm is usually implemented that enabled me to operate at better scale in this XSLT context. And then I will leave enough time for questions should there be any. Sequence alignment plays a big role in at least two domains, one of which is biomedical research, where people are interested in aligning genetic information. And in my world, I'm a historical linguist and manuscript scholar. In my world, we work with the alignment of words in variant manuscripts. So given several surviving medieval manuscripts that record the same text, each with little differences in the words that they contain and the order in which they appear and the like, I'm interested in finding programmatically the moments in these sources that should be compared. And from those comparisons, I then draw philological conclusions about the history of the transmission of the text. Sequence alignment is often divided into two types, global alignment and local alignment. And what's meant by global alignment is the alignment of entire objects, in my case, entire manuscript witnesses. What's meant by local alignment is finding moments of alignment within these larger texts. And a common philological context for local alignment would be text reuse. That is to say, in one text, finding moments where the author might cite another text. And when you do local alignment, it's without regard to global alignment. So they're really different types of tasks. Furthermore, alignment problems are usually divided into pairwise problems. We have two sequences we want to align, and what's called multiple alignment, or in philology, multiple witness alignment, where you have multiple witnesses, multiple texts that you wish to align. These turn out to be different problems. There are known algorithms that promise an optimal solution to pairwise alignment. Multiple witness alignment is an NP-hard problem that does not at the moment have let's say, a universally accepted optimal solution. There have been some attempts to address multiple witness alignment by applying pairwise alignment in a progressive or iterative manner. These have order effects. That is to say, if you align two witnesses into a sort of super witness and then fold in a third, you get a different result depending on the order in which you touch the manuscripts. This cannot be correct because the optimal alignment cannot depend on the order in which I touch the manuscripts. For this presentation, when I focus on Needleman Wunsch, I'm going to be focusing on pairwise alignment and furthermore on pairwise global alignment. I'm not going to speak about local alignment, and I'm not going to speak about multiple witness alignment. The point of alignment is to try to find the best alignment of the items that you are trying to compare. So I've put two words up here, and I am aligning at the character level. There are two A's in the first word. There is one in the second. So abstractly, I could align the A in the second word with either of the A's in the first word. But what I want to do is get the alignment that has the largest number of matches. Those are in green on the slide. The smallest number of mismatches, those are in red, and the smallest number of gaps. The scoring for this, that is to say how much credit you give to a match and how much discredit you assign to a mismatch or to a gap, is up to you. So the scoring system is in the hands of the person performing the alignment, and the decisions you make about how to assign these scores depends on what, in my case, on what I as a philologist think is the meaning of whether there is a gap in an alignment versus a mismatch. The known optimal solution to this problem is implemented in a context called dynamic programming, which dates to the early 1950s, where it was invented by Richard Bellman, who was working at that time at the Rand Corporation. And the idea behind dynamic programming is that if you have a large problem, there are situations in which you may be able to approach it by treating it as a bunch of small problems. But this is not simply divide and conquer. These small problems have certain properties that make them susceptible to dynamic programming. One is called optimal substructure, which means that the optimal solution to the big problem can be achieved through the optimal solutions to the subproblems. And if that's all there were, that could be divide and conquer. But then there's the overlapping subproblems, which is to say that you would have to perform the same computation multiple times, and by taking a dynamic programming approach, you avoid having that repetition. And we'll take a look at how that applies in the context of sequence alignment shortly. A common task, which is often introduced when one speaks of dynamic programming, is the calculation of a Fibonacci series. Each value in the Fibonacci series after the first two is the sum of the two that preceded it. And this goes on infinitely. And if you start calculating it, if I ask you what is the 10th Fibonacci number, you have to calculate the 9th and the 8th. Well, when you calculate the 9th, you also have to calculate the 8th and the 7th, so you're calculating the same things multiple times. So this is that overlap we talked about. And we're going to see where overlap also occurs then in a sequence alignment situation. The Needleman Wunsch argument, Needleman Wunsch algorithm, which I'm going to walk through in a moment, traditionally has the following steps. In this diagram on the screen, I am aligning the word koala along the top with cola along the left. And the first thing I do is I build a grid, and I write one of the sequences on the top, the other one down the left. I determine my scoring system. And for this alignment, I have decided that a match is going to have a value of +1, a mismatch of -1, so I want to penalize the score if I have a mismatch, and a gap of -2. So I would rather have a mismatch than a gap. There are other scoring systems. There are various ways people decide on their scoring system. What I've come up with is not radical, but it's not the only way one might have done it. So as part of the initialization, I have a grid, I have my sequences, and I then fill in the row below the top sequence and the row to the right of the left sequence with sequential multiples of the gap penalty. So my gap penalty is -2, therefore the sequences are -2, -4, -6, etc. Ignore for a moment those arrowheads. I'll talk about what those mean in a moment. So this is all initialization. I have my scoring system, I have my grid, I have my sequences, and I have initialized the first row and column with these multiples of the gap penalty. I then begin in the first intersection of the first sequence item on the top and the first sequence item on the left. So this is the intersection of this K and this C. And for each of these cells in turn, in my initialization, none of this stuff is here. All I've initialized is the top row and the leftmost column. So I start in the upper left corner of real data, and I want to introduce into that cell the highest of 3 values. One value is take the cell above and augment it by the gap penalty. So the cell above is -2, my gap penalty is -2, that value would be -4. So that's one candidate. Another one is the cell to the left, and I do the same thing. I augment it with the gap penalty, that's also -4. And the third value is the one that's diagonally above to the left, and I take that value and I augment it by either the match or the mismatch score, depending on whether these guys are the same. Well, K and C are not the same, it's a mismatch. My mismatch penalty is -1, so I augment my 0 with -1 and I write a -1 into the cell. Great, I have filled one cell, yay. I then proceed across the row cell by cell, and when I hit the right end, I go down to the next row and I keep going. The way I have color-coded this, each of these pinks is a mismatch, each of the greens is a match. So here's an O on the top, matching an O on the left. The reason you fill the cells in this way, according to the classic description of the algorithm, is that each cell depends on 3 values. 2 of them are in the row above, so as long as I'm going down row by row, I can guarantee that those values will be there when I need them. And the third value is the one to the left. So as long as I go across the row from left to right, I can guarantee that that one will be there. So this is the order in which I want to fill these. Those of you who have read Jenny Tennyson's postings from 2007 about calculating Levenshtein distance, also a dynamic programming algorithm, will recognize this approach. And I'm going to talk about what I learned from Jenny's postings and also how this problem is both similar and different to what she was trying to do. When I reach the bottom, when I reach the lower right cell, I have filled everything with a number. And I have a grid with a bunch of numbers. But I don't have a sequence alignment yet, and what I want to do is get from this grid that I just filled to this sequence alignment. So the next part of the Needleman Wunsch algorithm is you start in the lower right cell, and all you look at is where you took the value from. So this 0 in the lower right cell was determined by taking the best of the 3 values in the surrounding cells. The one above was -3. The gap penalty decreases that to -5. The one on the left was -2. The gap penalty changes it to -4. The one diagonally above to the left was -1. This is a match of A and A, so that's a match benefit. It goes up by 1. In other words, this cell was filled on the basis of the value that was here rather than the one that was there and there. And that's what these arrows mean. And in order to perform the final alignment, all I do is trace the arrows. And if the arrow comes from the diagonal, then I take one item from the end of each sequence and I align them at the end of what I've tried to produce. If, on the other hand, the value comes from the left, then I take an item from one sequence that's not matched by the other. So these top and left arrows are places where I have to introduce a gap, where I have a value from one sequence that doesn't correspond to the other. And by the time I have finished walking back through the grid and I've reached the upper left, I've aligned all of my items. It is possible for there to be ties. It is possible for the best value to come from more than one of those surrounding cells. In that case, they are all optimal, and you could follow all of them. I don't need all of the optimal solutions. I need one. In this case, there is only one optimal solution, but in the real implementation, the code is in GitHub. In the real implementation, I arbitrarily picked one, and that way I always wind up with one of the possible optimal alignments. One of the things that's helpful for me in this backward alignment is, in this backward traversal to perform the alignment, is that all I care about when I'm doing that is where the value came from. I don't care what the value is. I don't care what the sequence items are that were above and to that side. All I care about in this case is the direction of that arrow, and that's going to be useful later. So how do we do this in XSLT? Well, what we would like to do is take our empty grid and say for each intersection, go get the 3 surrounding values and fill it in. And that, of course, doesn't work with for each because for each doesn't proceed sequentially. For each is a functional expression, and for each of those cells, it will look all around, but when it gets to a cell, it doesn't have the value of the ones that were computed before it because they weren't computed before it. This is not the order of execution. This is just going to be the order in which the output is created. So if you try to do for each, you're not going to have access to all of those values. And How are you going to deal with this? Well, one way you could deal with it is with recursion, and this was Jenny's first solution to the Levenshtein distance problem, where as she walked across each row and then down the columns, for each one she called a recursive function, or maybe a recursive template, I don't remember which way she did that, passed in the values, so each one inherited what had happened before. This gets you very deep recursion, and deep recursion can be problematic. You can overflow your stack, you can try to work around that. And Jenny was working in XSLT 2.0, this was before XSLIterate, so in her first approach, the recursive strategy worked as long as you didn't run out of memory. In XSL3, of course, where you have XSLIterate, you don't have to worry about that stack problem. But what Jenny noticed in her second posting, which was like 3 days after the first one, was that there was a better way you could do this. And she noticed that, and we're looking at our grid again, traditionally, you approach these cells from left to right and from top to bottom. And if you do it that way, you have to recur on each cell. What Jenny noticed in her second posting was that if you think about this in terms of the antidiagonals, the diagonals that go from upper right to lower left, there are no mutual dependencies inside any of these. So if we take, say, the one that starts here and look at that antidiagonal, this one depends only on the stuff before it, this one depends only on the stuff before it, etc. So what Jenny did in her second approach was recur only on each antidiagonal, and within the antidiagonal, she used XSL for each. And that worked just fine because all of the information needed was present in the preceding two diagonals. So she had to pass those along, but what this did was change the recursion from quadratic, from recurring on each cell, to linear, from recurring on each diagonal. This was obviously a big improvement. We've then achieved an improvement in the depth of recursion, but if we go back and think about the traditional Needleman Wunsch algorithm with that backward traversal at the end, you have to accumulate the entire grid until you get at the end so that you can walk backward through it diagonally and so that you can figure out the path you took and thus align your sequence items going back one by one. This is a difference between Needleman Wunsch and Levenshtein. With Levenshtein, which proceeds the same way, all you care about is that number in the lower right cell, and you could just throw away the other stuff when you're done with it. But in classic Needleman Wunsch, you can't do that. You need the entire grid, and the entire grid is big. So what I tried to do as a way of improving this was that instead of accumulating the entire grid and walking back through it, what I stored on each cell in addition to its value was not just the cell from which it inherited, which is the classic approach. Rather, I stored the entire cumulative path. So as I got to each cell, if I got to this one, I didn't just store that it got its value from the left, I stored that it's got its value from the left, which came from up and diagonal, which came from the diagonal, which came from the diagonal. So I accumulated this full path. And what's helpful here then is because the calculations depend only on the two preceding diagonals, I don't have to pass the entire grid forward. All I have to pass forward are the two preceding diagonals. So the amount of storage is reduced enormously. It's only, basically I'm working with 3 diagonals at the time, the one I'm filling and the 2 that preceded it, because those hold all the values I need to calculate the values for the new one. Each of those has to be kept only for a 3 diagonal lifespan. Then I throw away the oldest one, add the newest one, and keep going. And when I get down to the bottom, I have this little baby antidiagonal with its 2 slightly older siblings preceding it. What I've done by doing this is remove the need to pass forward the entire grid. And in the published version of this report, where I have the timings, I found that when I was passing forward the entire grid at a certain point, and it was a certain fairly proximate point, I ran out of memory. And I had a machine with a lot of memory. And yeah, you could give it more memory, but at some point, you're going to run out of memory. So not having to save the entire grid and not having to pass that forward made it possible to align longer sequences than I would have been able to align otherwise. You still have to perform a calculation for every cell, so there's still a quadratic aspect to this. You have to look at each cell individually. And there are heuristic approaches that would let you eliminate certain paths ahead of time, but one of the reasons the Needleman Wunsch algorithm is guaranteed to get you an optimal solution is because there's no risk of missing anything. You look at every cell, you look at its 3 neighbors, and you perform the calculation. Oops, sorry. So you wind up with this kind of curve. And I ran this in both Saxon HE, that's the blue, and Saxon EE, which is the red. And I expected the EE to perform much better than the HE because, what do I know? Not a computer scientist. And within the antidiagonals, where I am using for each, I use the Saxon EE feature of Saxon threads, which let me specify, since those are all independent of one another, it let me specify that they could be calculated in parallel. Now, the documentation for Saxon threads warns you that whether you see an improvement in multithreading is going to depend on the amount of computation, among other things. There isn't much computation going on here. I'm looking at 3 values and I'm picking the best ones. So I knew going into this that this was probably not an ideal solution to benefit from multithreading. So after seeing that those curves were awfully close, I went back and checked the multithreading in a little more detail. So what you see in these little spark lines is I was aligning documents according to the number of paragraphs. I went from 1 to 15 paragraphs. The details about the test corpus are in the written paper. But that's what this 1 to 15 means. And what the spark line shows is, in the percentage, it's the variation between, I ran each of them 10 times, and it's the variation between 10 times and with 10 different thread settings. So this is with 1 thread, this is with 2, this is with 3, et cetera. So it's the variation between the best and the worst performance with the number of threads, and the percentage is how different those were. And most of them were pretty small, 3.9, 1.9, 2.6. The biggest one was 10.26 over here. But the other thing, and the reason I did this in spark lines, was that the directions are all over the place. And what this tells me is, and again, not a surprise when I go back and read the documentation, that this wasn't the kind of problem, because there wasn't much computation going on perhaps. This was not the kind of problem that was going to benefit from multithreading. So I'm quoting the conclusion of Jenny's second paper here, where she says that you want to iterate rather than recurse. And now that we have XSL iterate, we can do that, and we avoid any risk of the kind of overflow that you might get if you're doing recursion. And I'm implementing the antidiagonal traversal that Jenny used in that second solution. So I'm not recurring on every cell, I'm just doing it on, or I'm not iterating on every cell, I'm just doing it on every diagonal. But furthermore, and really the only part of this that is completely new is that, or at least it was new to me, was the idea of accumulating that entire path on the cells as I was building the grid, so that I could throw away those older diagonals and not have to pass the entire grid forward. And that's kind of all I have to say. Thank you for your attention.
Thank you very much. So we have time for questions. Okay, one from Mike, and then second. Next. So first Michael, then Nigel.
I skim-read your paper this morning, and it discussed something which I don't think you covered in your presentation, which is the actual data structures that you used. But I think you're using XML node structures for the intermediate data structures, aren't you?
I'm sorry?
You're using XML node structures for the intermediate data structures.
Yes.
And I just wondered whether you'd considered using the new data structures of maps and arrays instead, and whether that might give a difference.
I considered that only too late to implement it. What I used to build the grid was just a bunch of cell elements, each of which had information about its row and its column membership and some of its other properties. So it's not structured like the tables we're familiar with, where you have rows that contain cells. I didn't try to implement this with arrays or with maps. Should I?
Well, there were two things I was thinking. One is the data typing. You talked about numeric data types and conversion to strings and so on, which you inevitably get if you're using an XML representation. And the other was the question of making small changes to big structures, where with maps and arrays, certainly in the Saxon implementation, making a small change to a big structure is relatively cheap, whereas with XML it's quite expensive.
So this is the next version I should try. I did, where I stored the rows and columns, I had to calculate those values to find the neighboring ones. And this was my first experience with schema validation in XSLT. So I typed them, and that way I didn't have to do the conversions when I did the lookup. But I did read that appending an item to an array in Saxon is an inexpensive operation, and that made me realize that maybe that was something I should look at.
Which release you're using.
I'm sorry?
It depends which release you're using.
One of the other things that somebody pointed out too late for me to implement is that as I was building up this path, I was doing it as a sequence of characters. So D meant down and U meant up, or D meant diagonal or something. And string concatenation, of course, is, well, of course, once somebody pointed out to me, string concatenation is probably not the most efficient way to do this. I think the big expense is going to have to touch every cell in a quadratic structure, and so I'm not sure how much, I don't know of a way to get around that, but I do understand that there are opportunities for improvement that I should still explore. Thank you.
Hi, I was going to mention arrays, but Mike's already done that. A related thing, I wondered if you'd considered accumulators for recording the paths as you iterated through. Did you look at accumulators?
I didn't, should I?
Okay.
What?
Would they be useful, for example, for recording the iterative path you made?
I don't know. My guess is it would depend on how they're implemented.
Thanks.
Michael?
Okay. Yeah, please, Mike, wait and for microphone, so it's being recorded. Thank you.
I'm just saying using accumulators wouldn't have occurred to me, but it often doesn't. And people do achieve remarkable things with that amazing feature.
Okay, we still have time for one question. Anyone else? Okay. Okay, we have time for two questions, so ladies first.
Thank you. I was wondering, is there any benefit at all to working with n-grams rather than aligning on single characters? I mean, to some extent, is that what this is doing? And is there any benefit to looking at the value of a series of two rather than just the value of each one?
Possibly. I work on alignment in a different context. I'm one of the contributors to the Collate-X package, which is a Python implementation of alignment algorithm. And that does multiple witness alignment, and we play a lot of tricks there to try to make the data manageable. And basically, they're heuristics. And one of the reasons I wanted to follow this algorithm was that there's nothing heuristic about it. It's guaranteed to find you the optimal alignment. But that's one of the reasons it doesn't scale as well. And as you move up to it's quadratic. As you move up to larger data, either you're going to find a way to ignore part of the potential search space because it's unlikely to have the solution you want, or you're going to have to be able to deal with structures that grow quite rapidly in size.
Thank you.
And the last question?
So just, you mentioned, David, you're not a CS person, you're not an XML person, I guess.
I'm a historical linguist.
And which is great. And I really enjoyed the presentation, very masterful description of an algorithm. How did you choose XSLT?
XSLT is the programming language I know best, so it's the first place I look whether it's appropriate or not. But often I work with XML data as a document person, as a digital humanist. And many of the implementations of these alignment algorithms are intended to work on the equivalent of plain text. And then you have to jump through hoops to work around any markup. For example, you don't want to treat your XML as if it were plain text and wind up aligning on the angle brackets. That's not part of your data. And so what I had in the back of my mind was that if I did the alignment in an XML-aware context, I might be in an easier position to separate the markup information from the textual content, do the alignment on the textual content without losing the markup, and then put them all back together. But in order to do that, I had to come to an understanding of just, how this algorithm works, which was a lot of fun.
Okay, thank you very much again. Very interesting talk.
Thank you.